Welcome to Chapter 23, Graph Machine Learning. In this chapter, we learn how to work with data shaped like a network, where the connections between things matter as much as the things themselves. A great deal of the world is shaped like a network. This chapter is about learning from data that takes that form, where relationships, not just individual records, carry the signal. By the end of this chapter, you should be able to explain what graph-structured data is, describe nodes, edges, and directed and weighted graphs, represent a graph as an edge list or an adjacency matrix, and name the common graph machine learning tasks. You should also be able to compute and interpret degree, centrality, and page rank, explain what community detection does, describe node embeddings and graph neural networks in plain language, and build a graph in Network X to feed features into a classifier. This figure shows a transaction graph where each node is an account and each edge is a transaction. The two red nodes form a coordinated fraud ring, and what gives them away is their shared pattern of connections, not any single account on its own. So, what is a graph? At its heart, a graph is simply a structure for representing relationships between things. More formally, a graph G is a set of nodes V together with a set of edges E, where each edge joins a pair of nodes. The nodes stand for entities, and the edges stand for the relationships between them. Graphs are everywhere. In a social network, the nodes are people, and the edges are friendships. In a payment network, they are accounts and money transfers. The web, citation networks, and even molecules all share this same shape. The reason to reach for a graph is that in all of these settings, an entity cannot be fully understood in isolation. Its meaning comes partly from what it connects to. The node is the easy part. It is simply whatever entity you choose to track: a person, an account, a page, or a sensor. Edges come in two styles, and the difference matters. In an undirected graph, an edge has no arrow, so the connection runs both ways. In a directed graph, every edge points one way, like a follow or a payment. So far, an edge has only told us whether a connection exists, but often we want to say more than just yes or no. That is where weights come in. In a road network, an edge weight might be distance or travel time. In a payment network, the total amount transferred. And in a messaging or recommendation graph, the count of interactions. Weights let a model tell a casual acquaintance apart from a close friend, or a one-off $5 payment apart from a recurring $5,000 transfer. The strength of a connection becomes part of the data. Before a computer can analyze a graph, the graph has to be stored. An edge list simply records the connected pairs, while an adjacency matrix is a square table with one row and one column for every node. Let us look more closely at these two common ways of storing a graph. The figure shows the same small graph in both forms at once, so we can compare them side by side. Here is one graph in two representations. The edge list records only the pairs that are connected, which stays compact when most pairs are not. The adjacency matrix instead puts a 1 in each cell where an edge joins two nodes. Once your data is a graph, the questions you can ask fall into a handful of recurring shapes. Let us walk through the main ones. The core tasks are node classification, labeling each node, link prediction, guessing missing or future edges, graph classification, labeling a whole graph, community detection, finding densely connected groups, and anomaly detection, flagging the parts that look unlike the rest. The Cora citation network we use later is a textbook node classification problem. Each node is a paper, the edges are citations, and the goal is to predict each paper's research field. The simplest thing you can measure about a node is its degree, which is just how many edges touch it. In a directed graph, this splits in two. In degree counts the edges arriving, and out degree counts the edges leaving. Degree treats every neighbor as equal, which is not always right. Degree centrality measures popularity. Betweenness centrality measures how often a node bridges shortest paths. And closeness centrality measures how short its paths to everyone else are. Eigenvector centrality rewards being connected to other important nodes, not just to many nodes. PageRank is a famous variant of this, robust enough to rank the entire web. A node can score high on one measure and low on another. PageRank was invented to rank web pages, and its intuition is delightfully circular. A node is important if important nodes link to it. That seems to define importance in terms of itself, and it does, which is exactly why it works. That circular definition sounds impossible to pin down, but on a small graph we can solve it in just a few lines and watch the circularity resolve itself. This equation captures the idea. A node's page rank is the sum of the ranks flowing in from the nodes that point to it, each divided by how many outlinks that node has. Here, the term L of j is simply the number of outlinks leaving node j, which is how each node spreads its importance across its neighbors. Working through the small example, we substitute one equation into another and find that the rank of C equals the rank of A, which neatly agrees with where we started. The circular system is consistent after all. The result is satisfying once you read it. The same answer also emerges if you start every page at an equal 1/3 and repeatedly apply the equation, a procedure called power iteration that converges sweep by sweep. This figure shows PageRank on a 3-page graph computed by hand. Node size reflects rank. A and C tie at the top while B trails. Page C scores high because 2 pages link to it, and A scores high because an important page points to it. Community detection is usually unsupervised, a cousin of the clustering you met in Chapter 12, but on a network rather than a table of points. A word of caution, a detected community is a mathematical artifact, not a verdict, so human judgment still matters. Here is the most practical idea in the chapter, the one you can use tomorrow. You can compute simple structural features for each node, such as its degree, its page rank score, its clustering coefficient, its community membership, and the average degree of its neighbors. You can add betweenness or closeness centrality too. The trick is that you compute these once, attach them as new columns to your existing tabular data, and then train a model exactly as you always have. Here is the key point. You do not need a graph neural network to exploit a graph. Computing a few structural features and feeding them to a model you already know, such as XGBoost, is often the highest value, lowest risk way to add relational signal to a project. Handcrafted features are powerful but limited, since you can only add the patterns you think to measure. Methods like DeepWalk and Node2Vec instead learn embeddings by taking many random walks across the graph and treating each walk as a sentence of node names. Graph neural networks rest on a single guiding sentence. A node's representation should depend on its own features and on the features of its neighbors. That turns out to be exactly the right inductive bias for relational data. Most graph neural networks are built on message passing, and the recipe is simpler than the name suggests. Every node starts with a feature vector, gathers the current vectors of its neighbors, and aggregates them into a single message. The node then updates its own vector by mixing in that message and passing the result through a small neural network, and we repeat this for several layers. Each layer lets information travel one step further across the graph. This figure draws one layer of message passing. The target node, shown in orange, gathers feature vectors from its neighbors, aggregates them with a sum or a mean into a single message, and then updates its own representation. Graph methods earn their place wherever relationships carry predictive signal, catching rings of colluding accounts in fraud, powering recommendation through the user item graph, ranking search results with PageRank, and predicting molecular properties in drug discovery. They also drive knowledge graphs, cybersecurity, and logistics. The common thread is simple. If removing the relationships from your data would throw away information you care about, a graph approach is worth a look. Fraud is a relationship problem in disguise, which makes it one of the strongest use cases for graphs. The nodes are users, accounts, and devices. The edges are transactions and shared details. And once the graph exists, both of our toolkits apply. Graph machine learning is powerful but not free of trouble. Real graphs can reach billions of edges, straining memory. Missing or spurious edges quietly distort every metric, and a payment graph rewrites itself constantly, so a model can go stale fast. There are more challenges. Labels are often scarce, so methods must learn from structure with little supervision. Splitting a graph into train and test sets without leaking information is genuinely tricky, and relationship data is intimate, raising privacy concerns we return to in Chapter 24. Explainability is hard too, because a graph neural network's prediction depends on a whole neighborhood. Answering the question, "Why was I flagged?" is far tougher than for a simple model. Now let us get hands-on. We will work with Network X, the standard Python library for graph analysis. This code loads Zachary's Karate Club, a graph that ships with Network X, prints its node and edge counts, and then draws it using a fixed layout so the picture looks the same every time you run it. When you run it, you will see 34 nodes and 78 edges arranged in two loosely separated clumps, a hint of the structure we will uncover next. This code computes several structural measures for each member: degree, degree centrality, betweenness, and page rank. It then sorts the members by page rank and prints the 5 most central. The top of the list will be dominated by nodes 0 and 33, the two members who anchor the network's two sides. This code runs a modularity-based community detection algorithm to partition the members into groups, then redraws the graph coloring each node by the community it was assigned to. The detected communities line up closely with the historical factions that formed around the instructor and the club president, an unsupervised method rediscovering a real-world split. Next, we turn to link prediction, which asks which currently unconnected pairs are most likely to become connected. This code computes a Damik-Adar scores for the unconnected pairs, then sorts and prints the 5 pairs with the highest scores as the most likely future links. A high score means two members share many mutual friends without yet being connected, the network's way of suggesting you two should probably know each other. This is the same logic behind people you may know recommendations. To show the practical recipe, end to end, we load the Quora citation network, where each of about 2,700 papers is a node. Citations are the edges, and each paper carries one of 7 subject labels. This code loads Quora, converts it to a Network X graph, and builds a table of structural features for each node, including its degree, page rank, and clustering coefficient. It then splits the data so a random forest can be trained on those features alone. The payoff is striking. Using only structure, with no text from the papers at all, the model still does meaningfully better than random guessing across the 7 classes. Consider a case study. A fast-growing digital bank is losing money to organized fraud. Individually, the bad accounts pass every check with realistic names and valid documents. But the team suspects they are not acting alone, and they are right. The team builds a graph from data the bank already has, following 2 recipes from this chapter. They construct the graph from account, device, and transaction records, then compute features for each account such as degree, in and out degree, page rank, and community membership. They append those features to the bank's existing account data, train a gradient-boosted classifier on known fraud cases, and use community detection to surface suspicious clusters for human review, monitoring the graph continuously as fraudsters adapt. The payoff is real, and so is the danger. The code that follows demonstrates this fraud ring detection workflow on a synthetic transaction graph, using degree centrality as a simple anomaly score and click detection as a proxy for coordinated behavior. This code treats the Karate Club as a stand-in transaction graph, marks one faction as suspected fraud ring members, ranks the nodes by degree centrality, and then searches for large clicks that might represent rings of colluding accounts. Nodes that appear in large clicks and also score high on degree centrality are strong candidates for further investigation, showing how structural features can surface coordinated behavior that account by account checks would miss. This chapter introduced learning from data shaped like a network. We covered the vocabulary, the two standard representations, and the family of graph tasks. Then in Network X, we explored the Karate Club, rediscovered its split, ranked its leaders, and classified Quora papers from structure alone. For further reading, look to introductions on graph theory and network science, the Network X documentation and tutorials, and guides to PageRank and modularity-based community detection. The foundational papers on graph convolutional networks and on Graph Sage are well worth your time. You can also explore the PyTorch geometric documentation for scaling graph learning to large datasets, along with applied case studies on fraud detection and recommendation graphs. That brings us to the end of Chapter 23 on graph machine learning, where we learn to find signal in the connections between things.